In this video, I am going to give solution of exercise 1.1, which is on relations, and this is the second lecture on relations. And before we start solving, I am going to give a quick revision on relations, its different types and equivalence relation. Relation is any set of ordered pairs, which we have discussed in the first video about relation, all the explanations given there. So before this watching this video, you watch the first video once to have the concepts about relations. Ordered pair is any two elements written within first bracket is called an ordered pair. And any set of ordered pairs, that means any collection of ordered pairs, say 2, 3, 4, 5, another pair say 6, 7, and with this set of collection of ordered pairs, if we make a set, then this set, that is collection of ordered pairs, is called a relation. Then there are different types of relation. First is reflexive, and to understand reflexive relation, taking an example, a set A in which elements say only A, B, C, and the reflexive relation is, it is a relation, it is a set of ordered pairs in which for every element in the set A, the pair of identical elements. For A is there. For B, the pair made by BB is there. For C, the pair made by CC. For every element, the pair of identical elements must be there in the relation. And there may be more other elements, may not be more elements. Then this reflection is called relation is called a reflexive relation. Symmetric relation is, in a relation, if any ordered pair, say AB is there, and if AB is there, then the pair made by reversing the order, that means BA must be there in the relation. There may be more elements, may not be, but whenever you find a pair, then it's reverse pair, that means the pair reversing the order of elements must be there in the relation. Then the relation is called a symmetric relation. Transitive relation is like this. Say from A to B, B to C. I'll write a relation. If a relation in which AB is there, from A to B is there, then from B to C pair is there, then there must be the pair from the first to last, that means A to C. The pair made by first and last AC must be there. There may be other elements, may not be, but whenever we find two pairs in which the middle element is common, A to B, B to C, B is common here. So if we find an element common in both the pair, then the pair made by first and last must be there in the relation. Then the relation is called a transitive relation. The next is equivalence relation. If a relation can satisfy all the three conditions, that means the relation is reflexive, symmetric as well as transitive, then the relation is called a equivalence relation. Starting with the first question 1 of exercise 1.1, on the set A 1, 2, 3 up to 14, relation is given by R equal to the pairs xy in which xy are connected by this equation. All the pairs made by x and y in which x and y are connected by this equation. So 3x minus y is equal to 0. From here 3x is equal to y, that means y is equal to 3x. X can take the values from this set. That means x can take values 1, 2, 3, 4, 5 up to 14. Then what will be the corresponding values of y? Y is given by 3x. This is the equation. So y equal to 3x. Then what will be corresponding to 1? 1 3 is a 3, 2 corresponding to 3 to the 6, then 3 with 9, 4, 4 3 is a 12, 5 3 is a 15. But 15 we can take up to 12. 15 cannot be taken because 15 is going beyond of the set. According to question, the x and y, both the elements must be from the set A. So the relation is made by the pairs 1 3, 2 6, 3 9, 4 12, and 5 15 is going beyond of set, which cannot take. So this is the relation. But reflexive, we are going to check this relation if it is reflexive, symmetric or transitive. For reflexive, we know for every element in set A 1 is there, so 1 1 must be there in the relation. For 2 2 must be there in the relation, but we can say in the relation 1 1 is not there, 2 2 is not there, and hence the relation R is not reflexive. For symmetric, every element, every pair in the relation, for 1 3 belongs to the relation, the pair reversing the order, that means 3 1 must be there in the relation. But we can see 1 3 is in the relation, but the pair reversing the order 3 1 is not there in the relation, and we can show more example, and we can write therefore the relation R is not symmetric. For transitive, we can take these two pairs 1 3 and 3 9. 1 3 belongs to the relation, then 3 9 belongs to the relation, and then the pair for transitive, the pair made by the first and the last, middle one is common, the pair made by the first and the last, that means 1 9 must be there in the relation, but 1 9 is not there in the relation, and therefore the relation R is not transitive. So the given relation is reflexive, not reflexive, it is not symmetric also, it is not transitive. The next question is, in the set n of natural numbers, the relation is made by the pairs xy in which x and y are under these conditions. For x, first of all, x must be less than 4. Less than 4 natural numbers we can take only 1 2 up to 1 2 and 3. Then y corresponding values x plus 5. So corresponding to 1 plus 5 will be 6, corresponding to 2 plus, so it will be 7, corresponding to 3 value is 3 plus 5, that means 8. So the pairs are 1 6 2 7 and 3 8. So the relation is made by the pair 1 6 2 7 and 3 8, and then we can check for reflexive, symmetric and transitive. For reflexive, we know the pair of identical elements, for 1 1 1 must be there in the relation, for this 2 2 2 must be there in the relation, etc. But we can see 1 1 is not there in the relation, 2 2 also is not there in the relation, so the relation R is not reflexive. For symmetric, we can explain with this 1 6. 1 6 is there in the relation, but reversing the order, that means 6 1 is not there in the relation. Similarly, for 2 7 7 2 also is not there in the relation, and therefore the relation R is also not symmetric. For transitive, we have a definition 2 in transitive. Second definition I have given in the first video explanation. It is like this: if a pair AB is there in the relation and BC is not there in the relation, then the transitive pair from A to C also not there in the relation. AB is there but BC is not there, then AC also not there. In this case also relation R is transitive. It is by second definition. So in this case 1 6 is there in the relation, but with 6 some elements that we can write A not there in the relation, and therefore the pair made by the first and last 1A also not there in the relation. So by this definition the relation is transitive. Similarly, for second element 2 7 is there, with 7 no other pair is there in the relation. 3 8, with 8 no other pair is in the relation, and this both are also coming under this condition. So by this second definition the relation R is transitive, and hence the given relation is it is not reflexive, it is not symmetric, but the relation is transitive by this definition 2 of transitivity. The next question is 1 3. It is in this set A 1 to 6, the relation is made by all the pairs in which y is divisible by x. That means the second element must be divisible by first element. So we can write the relation and then we can explain. I have written the relation here, in which every second element is divisible by the first element in every pair. So if I start with 1, I can write 1 1 because 1 is divisible by 1. Then 1 2 also possible because 2 is divisible by 1. 3 also divisible by 1. 4 1. So I have written in which all the second element divisible by first element, starting with 1. Then starting with 2 again, 2 possible, yes, because 2 is divisible by 2. 4 is divisible by 2. 6 also divisible by 2. So with 2 starting, these are the 3 pairs, and so on for the remaining elements, in which I have written all the pairs. Second element divisible by first element. Second element divisible by first element. Now checking for reflexive. The reflexive condition is for every element in set A, I can take 1. The pair made by identical elements 1 1 must be in the relation, and hence it is there. 1 1 is there. For 2 also, 2 2 is there in the relation. It is belonging. For 3 also it is there, 3 3, and for 4 also 4 4, 5 5, 6 6. For every element we can write like this: for all element in set A, the pair made by the identical elements, they are in the relation 1 1 2 2 3 3. For every element it is there, and therefore the relation R is reflexive. Symmetric relation is for every pair I can take this 1 2. 1 2 is in the relation, then the pair made by the reversing the order, that means 2 1 must be in the relation. But we can see 1 2 is there, the pair made by reversing the order 2 1 is not there in the relation. And we can take more example, and even if we can show a single example in which the pair is not in the relation, we can say the relation R is not symmetric. For transitive, for every pair AB in the relation, BC in the relation, the pair made by the first and the last, that means AC in the relation, then the relation is transitive. Here we can take elements like I can take 1 3, and with 3, starting with 3 other pair, I can take this 3 6. 1 3 is in the relation, starting with 3, this is the pair 3 6 in the relation, and then the middle one is common, 3 is common in both, so the pair made by first and the last, that means 1 6 must be in the relation, and it is there, 1 6 it is there. Similarly, if we take any two pairs like this in which the middle element is common, then first and last there in the relation we can observe, and hence the relation R is transitive. We can explain with definition also. So the relation is transitive, and hence the given relation is reflexive. It is not symmetric, and it is transitive. The next question is, in set Z of all integers I have written here integers 0 1 2 3 positive natural numbers with negative of natural numbers makes integers, and the relation is made by all the pairs in which x and y are connected by this condition. Difference of x and y is an integer. Now reflexive, we should remember, reflexive, when we explain theoretically, we always take one arbitrary element from the set. We can take A. Symmetric, we can take 2 letters A B, and transitive we take always 3 letters A B C, and then we explain theoretically. We can take here x, we can take here y, we can take here, x y, 2 elements, and here we can take arbitrary 3 elements, say x y z, and then we can explain about the transitive condition. X reflexive, taking only x belongs to z integers, then x minus y is an integer. Here x is x and y also is x. We are taking the same element. So x minus y, that is x minus x, and x minus x is coming 0, and 0 is belonging to the set of integers. It is there in a set of integers. So if we take any element, since the difference is in the integer, so the pair made by the two elements x and x itself in the relation. We can explain with example, like if we take 2 difference with 2 itself, 2 minus 2 is 0, which is in the set of integers, so the pair made by 2 in the relation, and since it is satisfied for an arbitrary element x, that means it will satisfy for any element in z, and therefore the relation R is reflexive. The pair of identical elements, they are in the relation. For symmetric, if we have taken two elements, say xy belongs to z. If the pair xy to be in the relation, then the difference x minus y must be in z. It must be belonging to z. That means it will be some integer. We can take, say, k belongs to z. Then if we reverse the pair, taking minus common, reversing the pair is equal to k, and y minus x taking negative to right side, it is minus of k. And if k is any integer, minus of k also is integer. We can see here 2 is integer, 2 is in z, so negative of 2, that means minus 2 is also in z, and hence the pair yx also related, and hence the relation, therefore the relation R is symmetric. For transitive, taking three elements, can take, say, x, y, z belongs to the set of integers. If the pair xy belonging to the relation, then their difference must be some integer. I can take, say, k1 belonging to the set of integer z. If yz in the relation, then their difference y minus z must be another integer. Can take, say, k2 belongs to z. Then if we add these two equations, we are adding the two, that means x minus y plus y minus z is equal to k1 plus k2. Then y is getting cancelled, and then we are getting the difference of x and z. Difference of x and z is k1 plus k2, and k1 plus k2, that means sum of two integers. We can see sum of any two integer is again a integer, like 1 plus 2 is 3, it is again there in the set z. So k1 plus k2, sum of any two integer is again a integer. We can represent it by k, and therefore the pair made by x and z also in the relation, and hence the relation R is also transitive. So this relation xy made by the pairs in which x and y are connected by this condition, and this relation is reflexive, it is also symmetric, it is also transitive. So this relation, we can say it is a equivalence relation, and on equivalence relation we are going to solve more questions. In which a and b are connected by this equation, that is a less than equal to b square, and we have to prove that the relation is not reflexive, not symmetric, and not transitive. For not reflexive, I can take a 1 by 2. Then if 1 by 2 making the pair with itself, that means 1 by 2 to be in the relation, they must satisfy, this number must satisfy this condition, a less than equal to b square. That means 1 by 2 must be less than equal to 1 by 2 square. Here a is 1 by 2, b also is 1 by 2. But if we find 1 by 2, it is 0.5, and this is 0.25. So this number less than this number is not true. This is, in fact, it is bigger. So this is not true, this is not true. Therefore 1 by 2 pair is not there in the relation, and hence the relation R is not reflexive. For symmetric, taking the numbers minus 1 and 4, then minus 1, 4 belongs to the relation. Why? Because these two numbers, they are satisfying this condition. This is the condition. That means minus 1 less than equal to 4 square is true. These two numbers satisfying this condition. But if we are to have the pair reversing the order of elements, that means 4 minus 1 to be in the relation, then these two numbers also must satisfy this condition. That means in this case a is 4 and b is minus 4. So a must be less than equal to b square. But this condition is not true. 4 is not less than minus 1 square, and hence 4 minus 1 is not there in the relation. That means minus 1, 4 pair is in the relation, but the pair reversing the order is not there in the relation. Therefore the relation R is not symmetric. It is not symmetric. And to show the relation is not transitive, I can take the numbers. I can take the numbers 3, minus 4 and 1. Then 3 minus 4 belongs to the relation, because they satisfy the condition a less than equal to b square. This is true. And minus 4 1 also belonging to the relation because they also satisfy this condition a less than equal to b square. This is the condition a less than equal to b square, this condition. So first and second, 3 and minus 4 satisfying the condition, so they are related. Minus 4 1 also satisfying the condition, so they are also related. But if we take the first and the last, that means 3 less than equal to 1 square, 3 and 1, they are not satisfying this condition, it is not true, and hence 3 1 is not there in the relation, therefore the relation R is not transitive. So you have to keep in mind, whenever you are showing the relation is not reflexive, not symmetric, not transitive, that means when you are proving not, then we can take example, it is easier to solve, it is easier to understand. But if it is reflexive, symmetric, transitive, then we must explain with arbitrary elements, that is taking A, B, C, not by example. The next question is, in the set in which only few elements are there, 1 to 6, the relation is made by the pairs in which the pairs A, B are connected by the equation B is equal to A plus 1. And in this case only few elements, so we can write the relation and explain. Here A can take the values, A can take any value from this set, it can take value 1, 2, 3, 4, 5 or up to 6. Then what will be the corresponding values of B? B is given as A plus 1, B is A plus 1, so for 1 corresponding value will be 1 plus 1, it will be 2, for 2 will be 3, for 3, 3 plus 1 is 4, 4 corresponding value is 5, 5 with 6, 6 with 7, but up to 7 we cannot take because it is going beyond of the set, we can take up to 6. So the pairs are 1, 2, 2, 3, 1 with 2, 2 with 3, then 3 with 4, 4 with 5 and 5 with 6. This is the relation, all the ordered pairs we have found. Now we have to check the relation is reflexive or not. For reflexive, we know for every element in the set the pair of identical element must be there, but we can clearly see for 1, 1, 1 is not there in the relation, for 2, 2, 2 is also not there in the relation, and if we can show even for a single element the pair of identical elements not there in the relation, we can say the relation is not reflexive. For symmetric, we can take the pair 1, 2, 1, 2 is in the relation, but if we make the pair reversing the order of elements, that means 2, 1, it must be there in the relation according to the definition of symmetric, but the pair reversing the order is not there in the relation, and therefore the relation is not symmetric. And for transitive, we can explain taking pairs 1, 2, 1, 2 is in the relation, then with 2 starting another pair we have to take, and with 2 starting next pair is 2, 3, which is in the relation, but the transitive condition is the pair made by the first and the last must be in the relation, that means 1, 3 must be in the relation, but in this case 1, 3 is not there, and therefore the relation R is also not transitive. The next question is, in the set of real numbers the relation is made by all the ordered pairs A, B in which A and B are connected by the equation A less than equal to B. This is the condition which makes the relation, and we have to show that it is reflexive, it is transitive but not symmetric. And for reflexive, we know we have to take one letter. If we take arbitrary element and explain, we have to take A. For symmetric, we have to take 2 letters A, B, arbitrary elements, and transitive taking 3 letters, say A, B and C. And when it is not, then it is easier always to explain with example, which makes it easier to understand. So I can take example, say 1 and 2 in this case, but reflexive I cannot take example, I must show with arbitrary elements A. Now this is the condition, and if a pair AA is to be in the relation, then this A and A must satisfy this condition. That means A must be less than equal to A, and it is true. Less than or equal, there are two conditions. Out of the two conditions, less or equal, anyone is true means true, we can accept it. It is taken, it can be taken. So A less than true, less than A is not true, but A equal to A is true here. So A equal to A is true, then A belongs to the relation. It is satisfying this condition, and therefore the relation R is reflexive. Not symmetric, I can explain with example. So I have taken here 1, 2, and 1, 2, the pair is in the relation because they are satisfying 1 and 2, they are satisfying this condition. That means 1 less than equal to 2, it is true. Here equal to is not satisfied, but less is satisfied. And if we are to have the pair reversing the order, that means 2, 1 belongs to relation, then this 2, 1 also must satisfy this condition. That means 2 must be less than equal to 1. But here neither less nor equal, so no condition is true here. Therefore the pair 2, 1 is not in the relation, and hence the relation is not symmetric. And transitive, again we must explain with ABC, we cannot explain with example. So for transitive, if AB pair in the relation, then AB must satisfy this condition, that means A less than equal to B. And again, if BC in the relation, then B and C also must satisfy this condition. So B must be less than equal to C. Then clearly, if we have A less than B and B less than equal to C, then obviously A is less than equal to C. A less than equal to C. We can understand with example 2 less than 4, 4 less than 6, then obviously 2 is less than 6. It is true. So similarly here, if A is less than B, B less than C, obviously A is less than B, C, and hence the pair AC belongs to the relation. Therefore the relation R is transitive. The next question is, in the set of real numbers, again the relation is made by all the ordered pairs A, B, in which A and B are connected by the equation A less than equal to B cube. And again we have to check whether the relation is reflexive, symmetric or transitive. And to check reflexive, it is actually not reflexive. We can show taking an example 1 by 2. For reflexive, we know we have to take one element, arbitrary element, symmetric 2 arbitrary elements AB, and transitive 3 arbitrary elements AB, C. And for reflexive, taking 1 by 2, then if 1 by 2 is to be related with 1 by 2, then these two numbers must satisfy this condition. That means 1 by 2 must be less than equal to 1 by 2 cube. But this is not true. We can calculate the numbers and we can check. This is not less than this number, and hence 1 by 2 cannot be in the relation. Therefore the relation R is not reflexive. We can show with more numbers, and we can show with any real numbers less than 1. It will be not reflexive. It will not be satisfy the condition for reflexive. And to show symmetric, it is actually not symmetric, and that can be shown by example. -1, 4, this pair is in the relation because these two numbers, they are satisfying this condition A less than equal to B cube. It is true, they are satisfying this condition. But if we reverse the order, that means if 4 minus 1 is to be related, then these two numbers also must satisfy this condition. That means 4 must be less than equal to -1 cube, but this is practically not true. 4 is not less than this, and hence -1, 4 is there, but the pair reversing the order is not there, and therefore the relation R is not symmetric. And to explain about transitivity, I am taking three numbers 10, 3 and 2. Here 10, 3, this pair is related because they satisfy this condition. This is the condition, A less than equal to B cube. It is true. 10 is less than equal to 3 cube is true. So 10, 3 related. So first and second related. Now if we take second and third, that means 3, 2. They are also related because they are also satisfying the condition 3 less than equal to 2 cube. But if we take the first and the last, that means 10 and 2. If we are to have this pair 10 and 2, that means pair made by the first and the last, to be related, then they also must satisfy this condition. This is the condition a less than equal to b cube. But what we can see here is 10 less than equal to 2 cube. Is it true? No. 2 cube is 8, so 10 is not less, and hence 10 3 pair is there. 3 to 2 also pair is there in the relation, but the pair made by the first and the last, that means 10 and 2, which is not in the relation. Therefore the relation R is not transitive. The next question is, the relation is in this set 1 to 3. It is given by the pairs 1 2 and 2 1, and we have to check, we have to explain that it is not reflexive, it is not symmetric, and also it is symmetric but it is not transitive. We have to explain. Now for reflexive, we know it is for every element in the set the pair of identical elements must be there. For 1 1 must be there. For 2 2 must be there in the relation. For 3 3 must be there in the relation. If for every element the pair of identical elements are there in the relation, then we can say the relation is reflexive. But here we can see 1 1 is not there, 2 2 also not there, 3 3 also not there. Therefore the relation R is not reflexive. And even if it is not there for a single element, no need to show for all the pairs. Even if it is not there for a single element, we can say it is not reflexive. For symmetric, the definition is for every pair. Symmetric is not for every element in the set. It is for if an element is in the relation and pair is there in the relation, then the pair made by reversing the order also should be there in the relation. Like here 1 2 is there in the relation, and if we reverse the pair, then 2 1, which is also there in the relation. And if we take 2 1, then reversing is 1 2, and hence that is also true for both the elements. Therefore the relation R is symmetric. It is satisfying the condition symmetric. For 1 2 reverse is 2 1, and for 2 the reverse is 1 2, and for both the pair it is satisfying the symmetric condition. Now for transitive, 1 2 is in the relation, and with starting with 2, that means the next pair 2 1 is also in the relation. 1 2 2 1, and the pair made by the first and last, that means 1 1, also must be in the relation. Then only we can say it is transitive. But the pair made by the first and last, that is 1 1, is not there in the relation, and therefore the relation R is not transitive. So it is not reflexive but symmetric and not transitive. The next question is, the relation is made on set of books in a library. It is by this condition, two books are related in which the books are having same number of pages. If two books have same number of pages, means books are related, and we have to show that the relation is reflexive, it is symmetric, and it is transitive. We know for reflexive we have to take only one element, that means consider one book X in the library. Then for symmetric we have to take two books, and for transitive, to explain, we have to consider three books. Now reflexive, one books, and then we can say the book X and X itself have same number of pages. If we count number of pages in a book X, and again counting the number of pages of the book itself, obviously it is going to be same, and hence we can say book X and X have same number of pages. That means the book itself is related to it. So XX belongs to the relation, and therefore we can say the relation R is reflexive. To explain symmetric, we have to take two elements, that means two books in library. So we are taking two books X and Y, and if X and Y are in the relation, that means the pair XY belongs to R, then the two books X and Y must have same number of pages. Now X and Y have same number of pages, we can change the order. Y and X have same number of pages, and that means the books made by the pair made by the books YX also in the relation. That means xy belongs to R implies yx also belongs to R, and therefore we can say the relation R is symmetric. To explain transitivity, we must take three elements, and in this case, three elements are three books in library. So consider three books X, Y, Z are in library. Then, if the pair XY, that means two books X and Y are in the relation, then the two books must have same number of pages is the given condition. And if the books Y and Z are also in the relation, then they also must have same number of pages. Then obviously we can see here X and Y having same number of pages, Y, Z also same number of pages. So obviously X and Z must also have same number of pages, and it is written that X and Z have same number of pages, and whenever two books have same number of pages, they must be in the relation. And hence XY belongs to R, YZ belongs to R implies first and last, that means XZ also in the relation. Therefore we can say the relation R is transitive, and that means this relation is an equivalence relation. It is satisfying all the three conditions, reflexive, symmetric as well as transitive. So this given relation is a equivalence relation. The next question is, in this set of numbers 1, 2, 3, 4 and 5, the relation is made by all the ordered pairs AB in which modulus of A minus B is even. Now even numbers we know 0, 2, 4, 6 and all multiples of 2, and we have to explain that it is reflexive, symmetric as well as transitive. That means the relation is an equivalence relation. To explain reflexive, we have to take one element. We can explain this question, we can explain by writing all the ordered pair also, because only few elements, or without writing by ABC also we can explain. So I am going to explain with ABC arbitrary elements. So if it is reflexive, we take for one element and explain, and the element with itself, if the pair is to be in the relation, then these two must satisfy this condition. That means modulus of A minus B is even. They must satisfy this condition, A minus B, but here A is A and B also is A. So it is modulus of A minus A, and modulus of A minus A is 0. 0 is even. 0 is even. So modulus of A minus A is 0 is even, and hence A with A itself, the pair is in the relation. So the relation is reflexive. Like 1 minus 1 is 0, so 1 related to 1. 2 minus 2 modulus 0. 0 is also even, so 2 related to 2, and so on. All the elements are related to themselves. Symmetric we explain with two letters. I can take AB, and if the pair AB is in the relation, then they must satisfy this condition. This is the condition. That means modulus of A minus B is even. Then we can take minus common and we can reverse the pair. That is also even. And modulus of negative, if modulus of minus 2 same as modulus of plus 2, so modulus of negative same as modulus of positive, so I can make it B minus A is also even. And if modulus B minus A is even, that means the pair BA also in the relation, therefore the relation R is symmetric. To explain transitive, we have to explain with three elements. So I'll take ABC, and if the pair AB is in the relation, then A and B, that means modulus of A minus B, A and B must satisfy this condition. That means A minus B is even. If modulus of A minus B is even, then the number itself, that means A minus B is also even. If modulus of a number is even, then number itself must also be even. Same way, if we take BC pair is in the relation, then modulus B minus C is also even. And if modulus of number is even, then number itself is also even. Now if we add these two, that means if we add A minus B plus B minus C, here no modulus, only the numbers, then this is getting cancelled, and this is even, we have explained here. A minus B is even, B minus C is also even, so their sum also must be even. That means the sum of two even number is always even, which we know, and B is getting cancelled. Finally we are having A minus C is also even. That means the difference A minus C is even, then their modulus also must also be even, and modulus of AC also even. That means the pair AC is in the relation, therefore the relation R is transitive, and hence the relation is reflexive, symmetric as well as transitive, so it is a equivalence relation. In the second part is here to show that each element of this set related to each other. That means 1 is related to 3, 3 is, we have to prove that every element is related to every other element. Now if we take 1 and 3 and take the modulus, 1, 3 modulus is 2, it is even. That means 1, 3 pair is related. That means 1 and 3 are related. Now if we take 1 and 5, so 1 minus 5 is equal to 4 is also even. That means 1 and 5 are also related. Then if we take 3 and 5, 3 minus 5 modulus, we are always applying this condition A minus B, modulus A minus B, and we are taking here 3 and 5. The 3 minus 5 is again modulus is 2, positive, is also even. That means 3 and 5 also belonging to the relation, and hence every element of this set related to each other. 1 is related to 3, 3 related to 5, 1 related to 5. So all the elements are related to each other in this set. And then in the third part, we have to take element from this one element from this set and another element from this set, and then we have to show that they are not related. That means no element of this set related to element of this set we have to prove. Now we will take 1 with 4. So if we take 1 with 4, difference is 3. Modulus is always positive, which is not even. It is not even. That means 1 and 2 are not related. They are not related. Now if we take 1 and 4, 1 minus 4 is also, 1 and 2 we can take 1 with 2, which is equal to 1. That means again it is not even. So 1 and 2 are also not related. Same way we can explain. You can take 3 and 2. 3, 2 modulus difference is 1, which is also not even. That means 3 also not related to 2. 3, 2 not related. And we can, same way we can show for all the other elements, taking one element from first set, another element from second set, and we can show no element of this set related to the element of this set because their difference under modulus is not even. The next question is, in set A, x belongs to Z, in which x lies between 0 to 12. That means the elements will be starting from 0, 1, 2, 3, 4 up to 12. These are the elements in the set. And the relation is made by all the ordered pairs in which the difference between the two elements is a multiple of 4. Now multiple of 4 are 0, 4, 8, 12. These are the numbers which are multiple of 4. And whenever we find two numbers whose difference under modulus is any of these numbers, that means the numbers are related. And we have to show that it is reflexive, it is symmetric, it is transitive. We will explain with arbitrary elements ABC. For reflexive, we will take A belongs to the set A. That means A is representing any of these elements. Then under modulus, if the pair AAR is to be in the relation, they must satisfy this condition. Modulus A minus B is equal to any of these numbers. And here modulus A minus A is equal to how much? Modulus A minus A is 0, and which is there. That means it is a multiple of 4. So any number with itself under modulus difference is 0, so the number is related to itself, and hence the relation is reflexive. For symmetric, we have to explain with two arbitrary elements. We can take AB belongs to the set A. That means A and B are representing any two elements from this set. And then if the pair is in the relation, then modulus A minus B is multiple of 4. If modulus of A minus B is multiple of 4, we can take minus common and reverse the pair. Is also a multiple of 4. And we know modulus of minus x is same as modulus of plus x. So we can remove this minus sign, no problem. Then B minus A difference is also multiple of 4, and then the pair BA is also in the relation, therefore the relation R is also symmetric. For transitive, to explain, we have to take 3 elements. So we can take any 3 elements ABC in the set A, and then if AB in the relation, then their difference is a multiple of 4. If a number is multiple of 4, modulus of a number is multiple of 4, then the number itself is also multiple of 4. We can remove the modulus, no problem. Modulus of 4 is multiple of 4, so the number 4 itself is also multiple of 4. Then if the pair BC is in the relation, then their difference also under modulus is also multiple of 4. And if B minus C under modulus is multiple of 4, then the number itself is also a multiple of 4, and then we can add these two. That means A minus B plus B minus C. This is multiple of 4, this is also multiple of 4, and when we add any two multiple of 4 is also a multiple of 4. Like multiple of 4 is 12, another multiple is 8, so if we add 12 plus 8 we are getting 20, which is also a multiple of 4. And then here this is getting cancelled. Finally we are getting A minus C is a multiple of 4, and if a number is multiple of 4, then its modulus is also multiple of 4, and hence finally we are getting the pair AC also in the relation. Therefore the relation R is transitive, and hence the relation is an equivalence relation. Now in the second part, we have to write the equivalent class of 1. That means all those elements which are related to 1 under this condition. So if we can see 1 minus 1 is equal to 0, and 0 is a multiple of 4 here, that means 1 1 in the relation. Then with 1, what are the other numbers which will satisfy this condition? That means the difference is a multiple of 4, the number is here. We can have 1 and 5, modulus is again 4, difference modulus is 4, that means 1 and 5 also related. Then what are the other numbers? 1 with 9 also will be possible, difference is 8, is a multiple of 4, that means 1 and 9 also in the relation. Then 1 with next number will be 13, which is not there in the set, so we will have only these numbers, that means 1, 5 and 9. So we can say equivalence class of the element 1 is the set of all those elements related to 1, and here 1, 5 and 9 are related to 1, so it is the set made by 1, 5 and 9. So this is the complete solution to the question. The next question is, in the set of all points in plane, the relation is made by all the pair of points. 2 points are related if their distance from origin equal. I am explaining with example with a diagram. 2 points, if we take any 2 points P and Q, they are related if their distance from origin equal. That means OP equal to OQ, and we have to show that this relation is an equivalence relation. For reflexive, we have to take a single point. I am taking a single point in this plane. Then we can we can say this distance OP, the distance of P from origin is same as distance of P from origin. So we can say OP is equal to OP. That means the point P is related to itself, and therefore the relation R is reflexive. And for symmetry, we have to explain with 2 points. So if we take 2 points on plane, and if the 2 points are related, then OP must be equal to OQ by the given condition. Now taking 2 points in which OP is equal to OQ, then obviously we can say OQ is also equal to OP. Distance of Q from origin is same as distance of P from origin. That means we can reverse the order, and hence the points Q and P made the pair which is also in the relation. And for transitive, we have to explain with 3 points. So let us take 3 points P, Q and M on a plane, and if the pair PQ is in the relation, then this 2 points distance from origin must be equal. That means OP must be equal to OQ. These two distances must be equal. So OP is equal to OQ. Then if we take the pair made by second and third, that means Q and M also in the relation, then these 2 points also distance from origin must be equal. That means OQ must be equal to OM. These two also must be equal. OQ is equal to OM. Now clearly in the diagram we can see, if this distance equal, again this equal to this, then the first and the third must also be equal. Clearly the first and the last, that means OP must be equal to OM. First and the last, first equal to second, second equal to third. Obviously first and third are equal, which implies that the pair made by P and M points also must be in the relation. Therefore the relation R is a equivalence relation, because it is transitive, and hence it is a equivalence relation because it is satisfying all the three conditions, that is reflexive, symmetric as well as transitive. So it is an equivalence relation. In the next question, the relation is on set of all straight lines in plane, in which the two straight lines are related if they are parallel, and we have to show that the relation is an equivalence relation. And for reflexive we have to take one straight line, say L, and we can say clearly a straight line is parallel to itself. Every straight line is parallel to itself is true because the direction remains same, and then the pair made by the line with itself is in the relation, and hence the relation is reflexive. For symmetry we will consider two straight lines L1 and L2, I have shown in the diagram, and then if the lines L1 L2 making the pair is in the relation, then L1 must be parallel to L2 by the given condition, and if L1 is parallel to L2, obviously L2 is also parallel to L1, as we can see easily clearly in the diagram. If 1 is parallel to 2, obviously 2 is also parallel to 1, and then we can say the pair made by L2 L1 is also in the relation, and therefore the relation is also reflexive. And to show transitive, we will take three straight lines L1, L2 and L3 on plane. Then if the pair L1, L2 in the relation, then L1 must be parallel to L2 by the given condition of the relation, and if L2, L3 also in the relation, then L2 must be parallel to L3. We can clearly see in the diagram. If 1 is parallel to 2, 2 is parallel to 3. Then L1 parallel to L2 and L2 parallel to L3. We can clearly see in the diagram, which obviously implies L1 parallel to L3. And then we can say L1 L3 making the pair also in the relation, and hence the relation R is a transitive relation. And so the relation is satisfying, reflexive, symmetric as well as transitive, and hence it is an equivalence relation. And the second part, a straight line is given by this equation y equal to 2x plus 4, and you are asked to find what are the lines related to this. The set of all the lines related to this will be parallel lines, because condition is two lines related, which if the lines are parallel. So with this line, related lines will be all the parallel lines, say this one, all the parallel lines will be related to this line. And set of parallel lines represented by equation in which xy terms will be exactly same. So this straight line is represented by y equal to 2x plus 4. So all the parallel lines will have equation in which x and y terms will be exactly same, and only difference will be in constant terms, some constant k, where k belongs to any real number, and this will give the set of all those straight lines which are related to this line. That means this all the straight lines which are parallel to this line. And once again I am telling, the parallel lines x and y terms, the equations x and y terms must be exactly same. The difference will be only in constant terms. Constant, where k is any constant, that means it is a real number. In the next question, the relation is made by two triangles in which the triangles are similar. It is on the set of all triangles on a plane. in which the triangles are related if they are similar, and we have to show that the relation is an equivalence relation. That means it must be reflexive, symmetric, as well as it must be transitive. And to explain reflexive, consider one triangle T, one plane. I have drawn the diagram, and then we know every triangle is similar to itself. Clearly, every triangle is similar to itself. Therefore, we can say the triangle with itself making the pair is in the relation, and hence the relation is reflexive. And to explain symmetric, we'll consider two triangles T1 and T2 on plane, and then if the pair T1 T2 in the relation, then according to the definition of the function relation given, the two triangles must be similar. Similar triangles means sides are proportional, but here we are not going to show mathematical calculations, only we are giving the logical explanations. So if two triangles are in the relation, then according to the given definition of the relation, the two triangles are similar. And then if T1 is similar to T2, obviously T2 is similar to T1, and hence we can say the pair made by T2 T1 also in the relation, and hence the relation is symmetric. To explain for transitivity, taking three triangles on plane, consider three triangles T1, T2 and T3 on plane. Then if the pair made by T1 and T2 in the relation, then the triangle T1 must be similar to T2 by the given condition. And then if the second and third, that means T2 T3 making the pair is in the relation, then T2 must be similar to T3 by the given condition. And from the geometry, concept of geometry, we can say if T1 is similar to T2 and T2 similar to T3, then obviously the triangle 1 must be similar to 3. We can easily prove it geometrically, but the geometrical proof is not necessary here. We are just explaining with logical reasoning. So we can say T1 is similar to T2, and hence the pair T1 T3 is in the relation. Therefore the relation R is transitive, and hence the given relation satisfying all the three conditions. That means it is reflexive, it is symmetric, it is also transitive, and hence the relation is an equivalence relation. Now in the second part, three triangles are given, T1 with sides, T2 with sides length, and T3 with length of sides, and we are asked to check which two triangles are here similar. They are related. Related means similar in this condition. Triangles are related if they are similar, and we know similar triangles sides must be proportional. And if we compare here first and third triangle, we can see 3/6 ratio and 4/8 ratio and 5/10 ratio. These ratios are equal, 1/2, 1/2, 1/2. So ratio proportional equal is given by first and third triangle. Their ratios length of sides are equal. Each ratio is equal to 1/2, and hence we can say T1 and T3 are related, similar. That means T1 and T3, the two triangles are related. That means the pair is belonging to the relation. But if we see first and second triangle, we consider if we compare, they are not satisfying this proportional condition. This also not satisfying the proportional condition, and hence here only first and the third satisfying the proportional condition, and hence first and the third they are related. So this is the end of lecture 2, and in the next lecture, the lecture 3, we will have the solution of miscellaneous exercise along with higher level questions.